Simple harmonic motion involves regular repeating movements back and forth. We will illustrate this here using the trolley tethered between two sets of springs. When we pull the trolley back to one side here, we can see we displace the trolley to the right. What we will see is we will have a resultant force acting on the trolley. This is because the springs on the left are extended more than the springs on the right, and so the tension acting on the trolley to the left is greater than the tension acting to the right, hence the resultant force to the left. And if we were to release the trolley from this position, that resultant force is going to yield an acceleration acting to the left. Now initially the trolley then is stationary the moment we let it go, but that acceleration soon gives the trolley a velocity acting to the left. As it moves right to left across the track there, we will eventually reach the middle of the oscillation, what we would call the equilibrium position. Both sets of springs now are equally extended, the resultant force is zero, there's no acceleration, but we've got a maximum velocity to the left. And that moves the trolley across to this leftmost position. Now in this situation now, the springs on the right are extended more than the springs on the left. The tension acting to the right then, much greater than the tension acting to the left. This time, the resultant force acts to the right. That will again now cause an acceleration acting to the right, but at this particular moment in time, the trolley is changing direction, so its velocity is actually zero. So what we can see here is we have a maximum displacement in one direction, in this case to the left, the maximum acceleration, the maximum resultant force, they're both acting in the opposite direction. We can continue the motion on, and what we will see then as we come back through the equilibrium, this position, the equilibrium position is the middle position, this time travelling in the other direction. Once again, now we've got a maximum velocity, but this time to the right. Because the springs are both equally extended, there's no resultant force, there's no acceleration in that position, and that moves us then across to the right hand side. Then we get to the extremity of the position, extremity of the displacement on the right hand side. This time again, the resultant force is acting to the left, acceleration to the left, displacement is to the right, and we can see then the trolley will oscillate backwards and forwards. Notice, as frictional forces oppose the motion, energy is removed from the system. The amplitude of the oscillations, the amplitude would be the maximum displacement from equilibrium position. The amplitude does decrease over time, and this is due to the fact that energy is being removed from the system. However, the period of the oscillations will remain the same, and the reason for that is the amplitude decreases. Obviously the trolley is moving through a smaller distance during each oscillation, but because the amplitude is less, the springs aren't extended as much, you don't get as much resultant force, you don't get as big a maximum acceleration, you don't reach as big a speed in the middle. So although you're not travelling as far as the amplitude reduces, you're covering that distance at a slower speed. So it works out that the period is actually unchanged. So this is what we're seeing here. Basically the acceleration is really proportional to the displacement. If I extend the springs twice as far, I'm going to get twice the resultant force, I'm going to get twice the acceleration. So the acceleration is proportional to the displacement from equilibrium being the midpoint of the oscillation. The acceleration is proportional to the displacement, but it is in the opposite direction to that displacement. So if I displace the springs one way, the resultant force and the acceleration is actually acting in the opposite direction. And we can see that go again then. The trolley oscillates backwards and forwards a number of times until eventually all its energy is dissipated by frictional forces into heat. So we can say that for a body performing simple harmonic motion, acceleration is actually proportional to the displacement, but is in the opposite direction to the displacement. And that's a 2-mark question there for giving the definition of simple harmonic motion. If we're asked to define it, we need those 2 points. The acceleration will be proportional to the displacement. If I displace that trolley twice as far, I would extend the springs twice as much, and from Hooke's law that would give us twice the force. Twice the restoring force will produce twice the acceleration. Always remember that for simple harmonic motion, yes, the acceleration is proportional to the displacement from equilibrium, but it is in the opposite direction. And that's why when we look at the formula, there's a minus sign in it. A is proportional to minus x. X is the displacement from equilibrium. The minus sign there indicates that the acceleration is in the opposite direction to that displacement from equilibrium. We can rewrite that equation as A equals minus some constant times x, and that constant is 2 pi f all squared, where f would be the frequency of the motion. For simple harmonic motion, we can define the amplitude for a system, or for a body performing simple harmonic motion, which is simply the maximum displacement from the equilibrium position. The equilibrium position being the midpoint of the oscillation, where the forces acting on the object are balanced and the acceleration is 0. Because we know that the maximum acceleration will always occur at the amplitude position, this is the maximum displacement from equilibrium, we can write an equation and say A max, the maximum acceleration, will be 2 pi f all squared multiplied by the amplitude. Obviously, the biggest acceleration is when we've got the largest displacement. Always remember though, we're going to have a minus sign in there because we know that the acceleration will be in the opposite direction to that displacement. Of course, when the displacement is 0, that is, we're at the midpoint of the oscillation, what I would call the equilibrium position. At that point, x will be 0, and so the acceleration will be 0. As we've seen for the trolley there, tethered between those two sets of springs in the midpoint, the forces acting on the trolley are balanced. The tension in the springs pulling one way is balanced by the tension in the springs pulling the other way. There is no resultant force, there is no acceleration. So let's go back to our defining equation of simple harmonic motion. A is proportional to minus x. Acceleration is proportional to the displacement but in the opposite direction. Sometimes we might be asked to sketch a graph of acceleration against displacement for a body performing simple harmonic motion. Well, what's that going to look like? Well, we know it's going to be a straight line graph if they're proportional. We know it's going to be a straight line through the origin. But we also know it's going to have a negative gradient because of the minus in there. So if we're going to have a straight line through the origin with a negative gradient, it's got to look like this. We can see the drawing here. What we might sometimes be asked is, from a sketch of acceleration against displacement, or from a graph of acceleration against displacement, we might be asked to work out the frequency of the motion. Well, we can do that quite easily. So you see here in this example, we have a maximum acceleration for a body performing SHM of 120 meters per second squared, and at that point the displacement is half a meter. So when it's displaced half a meter one way, the acceleration is 120 meters per second squared in the opposite direction. Now, if we want to find the frequency of that motion, all we actually need to do is to find the gradient of the graph. So here we take the defining equation of simple harmonic motion, A equals minus omega squared x, where omega is called the angular velocity and is simply equal to 2 pi f. F, of course, is the frequency of the motion. Now, if we compare that to the general form of a straight line graph, y equals mx plus c, where y is what we have plotted on the vertical axis, x is what we have plotted on the horizontal axis, and m is the gradient of the graph. We can do a comparison here of the two equations. So displacement is plotted on the x-axis, acceleration is plotted on the y-axis. The gradient then is whatever is multiplying our x variable, which in the case of our equation here for simple harmonic motion, we can see that that is 2 pi f all squared. And so the gradient of our graph must be equal to 2 pi f all squared. So we can simply set the gradient, which in our case here, vertical step over horizontal, it's 120 over 0.5, has to equal minus 2 pi f all squared. And then we can simply rearrange that in order to determine the frequency of the motion. And so we'll do that here. And in this case, we reach an answer of 2.5 Hertz. So there we are, graph of acceleration against displacement, straight line graph it has to be, but with a negative gradient going through the origin. It has to look like that. We can label, as we've done on the graph, the maximum acceleration, the maximum displacement from equilibrium. So here we've written out our defining equation of simple harmonic motion again, A equals minus 2 pi f all squared x. That represents a differential equation, and it can be solved. We don't need to know how, but we just need to know that it can be solved to give us another equation for the displacement from equilibrium after a time t, and that is x equals a cos omega t, where omega is 2 pi f. A is the amplitude of the motion, and t is the time that has elapsed since we passed through a position of maximum displacement. So when we're using x equals cos omega t, what we must remember is x is always the displacement from equilibrium, but t is the time since the object was released from a position of maximum displacement. So at t equals 0, basically you're releasing it from an amplitude position, but you are always measuring x. X is the distance from equilibrium here. So for example, if we put t as 0, cos of 0 is 1, so at t equals 0, x, the displacement from equilibrium, will equal the amplitude. And that equation is in your data book. However, of course, often in simple harmonic motion we begin timing not at the end of the oscillation, but from the equilibrium point. So we begin timing as it passes through the equilibrium position, the centre of the oscillation. So in that case, instead of using x equals a cos omega t, we would have to use x equals a sine omega t, because obviously sine of 0 is 0. So if we start with t as 0, when we take sine of omega t we get 0, and therefore x will be 0. So obviously if we begin timing at the centre of the oscillation, we need x to be 0 when t is 0, so we use x equals a sine omega t, and there we are. So basically if you want to work out the displacement after a certain period of time, if you begin timing at the end of an oscillation, you need to use x equals a cos omega t. If you begin timing at the centre of the oscillation, you need to use x equals a sine omega t. In both cases, when you work out x, you will be working out the displacement from equilibrium. When you work out x, if you come out with a minus sign, if you come out with a negative value of x, that just means you're on the opposite side of the equilibrium position from where you started. So always remember, when you work out x, whichever of those equations you are using, you are calculating the displacement from equilibrium, the displacement from the centre position of the simple harmonic motion. Okay, while we're on equations of simple harmonic motion, there's a few more that we need to know about. As well as working out the displacement, we can also work out the velocity of the object performing simple harmonic motion. And we can do that using the formula here. So once again, omega is angular velocity given by 2 pi f, a is the amplitude, and x is the displacement from equilibrium. So if we know the displacement from equilibrium, we know the amplitude, we know the frequency of the motion, we can always work out the speed of the object at that point. For example, when x is 0 at the centre of the oscillation, we can put x in as 0, and obviously we will just come out with v equals omega multiplied by the square root of a squared, and the square root of a squared is just a. So the maximum speed of an object performing simple harmonic motion is simply given by angular velocity times a, or 2 pi fa, where a is the amplitude, f is the frequency of the motion. We will need to use that quite a lot. Just remember that the maximum speed is always at the centre of the oscillation, always in the middle. Acceleration is 0 in the middle, but the maximum speed is found in the middle. And of course all of those equations are on our data sheet, so we don't need to remember them, but we do need to know that they're there, and we do need to be able to use them. Okay, well, what about graphs of simple harmonic motion? What we have here is a graph of displacement against time for a body performing simple harmonic motion. Perhaps not very well drawn, but I did my best drawing it freehand. Now, what I'm doing here with the dotted line, clearly, usually, as we saw earlier on with the trolley tethered between the springs, the amplitude dies down over time, and the reason for that is what we call damping, resistive forces that oppose the motion and gradually reduce the kinetic energy of the object. And so here the full line represents an undamped system where there's no energy loss. The dotted line represents a more commonly seen system where we actually have some damping taking place. Now when that happens, the amplitude will die down during each oscillation. But one thing to make sure you always remember is that the period will stay the same. Alright, the amplitude might be dropping, and you might think, well, okay, I've got a smaller amplitude, it's not moving as far now. That was that trolley moving between those two points. As it oscillates backwards and forwards, it's travelling through a smaller distance on each subsequent oscillation. You might think then the time to do that would reduce, but in actual fact, of course, because its amplitude is less, it just has a smaller maximum acceleration at the ends of the motion. That means it has a smaller maximum velocity in the centre. So because its average speed during the oscillation now will be less, it actually works out that it's going to take exactly the same amount of time to cover that smaller oscillation. And so the period must stay the same. So you can often be asked, given a displacement time graph, what will that like if damping is present? Well, you should see the amplitude dying down by about the same fraction on each oscillation, but the period must stay the same. So notice here when I've drawn the dotted line, I've been very careful to keep the period the same. That is crucial. For simple harmonic motion, the period is unchanged even as the amplitude of the oscillations dies down due to the presence of resistive forces, what we would call damping. Of course, what we can also be asked to do is to draw velocity time and acceleration time graphs. And quite often we might be asked to draw those starting from a displacement time graph, and so we need to be able to synchronize them properly. Now always remember, for motion graphs, velocity is the gradient of a displacement time graph and acceleration is the gradient of a velocity time graph. So if I'm asked to plot the velocity time graph here from this displacement time graph, what I'm doing is just going down here, going down the graph and thinking, right, what is the gradient of the displacement time at each of these points? Where the gradient is 0, my velocity will be 0. Where the gradient is maximum negative, as it is in that second point, I'm going to have a maximum negative velocity. Gradient 0 again, 0 velocity. And where the displacement time graph has got its maximum positive gradient, maximum positive slope, that's when I'm going to have a maximum positive velocity. So I can plot those points basically and then draw my curve through those. Same thing for acceleration time. I've just got to look at my velocity time graph here. Wherever the gradient of my velocity time graph is a maximum positive, I'm going to have a maximum positive acceleration. Wherever the gradient of the velocity time is 0, my acceleration will be 0. And whenever I've got a maximum negative slope, downward slope, that's when I'm going to have my maximum negative acceleration. So I can see here going left to right acceleration time. From velocity time, I've got a maximum negative gradient on the velocity time. Then I've got 0 gradient on the velocity time, so 0 acceleration. Then a maximum positive velocity on the velocity time, and so a maximum positive acceleration. I can plot those points, draw the curve through them. Notice that when we've done that, basically the acceleration time graph is the same as the displacement time graph, but mirrored in the time axis. And that really follows from our definition of simple harmonic motion. Don't forget that acceleration is proportional to the displacement, so when the displacement is biggest, the acceleration will be biggest, but it's in the opposite direction. So when the displacement is positive, you know that the acceleration has to be negative. When the displacement is negative, the acceleration will be positive. And so there, just compare the displacement time graph and the acceleration time graphs, and notice that they are basically mirror images in that time axis. Okay, so we have a question here where basically we've got a trolley tethered between two sets of springs, and we're asked how we would find the period. So if we were going to do this, the first thing we would do is to set up what we would call a fiducial mark, some sort of mark. It could be a pin just in a bit of plasticine or something, just to mark the centre of the oscillation, so we know where the centre of that oscillation is. And we would then give it a displacement, set it into motion. We would get used to actually watching the oscillations. We would what we call count ourselves into the first oscillation, so -3, -2, -1, 0 as it comes through the centre. And on 0 we would start our stopwatch, and then we would count for a number of oscillations. Now one full oscillation is from the centre to one side, back to the other side, and back to the middle. So it's back to the middle again, but moving in the same direction as it was when we started out. That would be one oscillation. And what we would do is we would record a large number of oscillations, typically 20. We would do that several times. We would then take an average. So let's imagine we'd done that. We'd set up our fiducial mark, we'd given an initial displacement, we'd watched the oscillations for a while, we'd counted ourselves in, we'd begun timing at the centre of the oscillation, timed for 20 oscillations, repeated that a number of times, and we've got an average time for 20 oscillations here of 14.89 seconds. So if we divide that by 20, what we can do is to get the time for one oscillation, and we come out here, as you can see, at 0.74 of a second. So there we are, we've done a simple experiment, we've determined the period for this trolley, moving with simple harmonic motion back and forwards, left and right. What we could then be asked is, well, let's say we gave the trolley an initial displacement of, for example, 0.12 of a metre, and then we released it. What about then we could be asked, for example, to find the maximum velocity or maximum speed, if you like, of this trolley, which would occur obviously at its equilibrium position as it passes through the middle. So what's the maximum speed of that trolley going to be? Well, we could work that out. We've got a formula, it's in our data book, you look it up, and that is that Vmax is simply equal to omega A, or 2 pi f A, since angular velocity is just 2 pi f. The frequency here we can work out easily. If we know the period, frequency is simply 1 over period. So all we have to do is 2 times pi times 1 over 0.74 multiplied by the amplitude. Now if we've given it an initial displacement, the amplitude, at least initially, will be 0.12 of a metre. And we can simply then multiply all that together, put it in our calculator, and we will work out a maximum speed, which in this case comes to be 1.0 meters per second. Of course, as the amplitude dies down and decreases from 0.12 of a meter, if resistive forces and damping are present, what will happen is the maximum speed at the centre will also decrease during each subsequent oscillation. But as we've said before, the period of the oscillations is not affected by the amplitude, so that will remain the same. The period will stay at 0.74 seconds even as you start to see the amplitude of the oscillations die down. We could then be asked to work out the maximum acceleration here of these oscillations of the trolley, and that would also be straightforward. We know that for simple harmonic motion, acceleration equals minus omega squared x, or if you like, minus 2 pi f all squared x. Now if we just want to work out the maximum value of the acceleration, the magnitude, we don't need to worry about the minus, the direction is unimportant, we just want to know the maximum size. So what we've got here is 2 pi times 1 over 0.74, again frequency is 1 over period. Do remember to square that. Quite often students will lose marks just because they will forget to square 2 pi f, and obviously the 2 pi f has to be in brackets and then squared. We multiply that by the amplitude, and again we will work out a maximum acceleration, and in this case we have got 8.7 meters per second squared. So while the amplitude stays at 0.12 meters, that will be the acceleration there in those amplitude positions. If the amplitude decreases, well then so the maximum acceleration will as well, but the period again stays the same. So another thing we could be asked to do is to find the displacement of an object performing simple harmonic motion a certain time after release. In this example we're asked to find the displacement of the trolley 2 seconds after release, and so we will use the formula x equals a cos omega t, because we need x to equal a when t is 0. So cos 0 is 1 and x would equal a then. All we need to do is to put the numbers into that equation. Displacement is going to be, or the amplitude is going to be 0.12 meters. Omega 2 pi f, or frequency, is 1 over 0.74, and putting the time in as 2 seconds. And if we work that out, we will get 0.035 meters, or minus 0.035 meters. And the minus indicates that the displacement is now on the other side of the equilibrium position to where we released the trolley. So if we released the trolley from a position of displacement to the right, it's now displaced 0.035 meters to the left of the midpoint, to the left of the equilibrium position. One thing that I have to emphasize when you're using that equation is to make sure that your calculator is in radian mode. These equations here of simple harmonic motion assume that angles are going to be measured in radians. If you've got your calculator in degrees, you're going to get an incorrect answer, you're going to get a strange answer. So you might just need to go to the menu button and just check that you've got your angles being measured in radians on your calculator. A common loss of marks is just to forget and to have your calculator in degree mode, and it won't work. So make sure radians if you're using x equals a cos omega t. What we have here is an acceleration time graph for the motion of the trolley as it oscillates, and what we may then be asked to do is to produce a velocity time graph from that. We're really working backwards here because we know it is the gradient of the velocity time that gives us acceleration. So the way to think about this, to make sure that they are synchronized correctly, is that when we draw our velocity time graph, we need the gradient of the velocity time graph to have a maximum value at t equals 0, because we can see here the acceleration has got its maximum value at t0, so the gradient of our velocity time graph must be a maximum at that point. A quarter of a cycle in, the acceleration has dropped to 0, so we know that the gradient of our velocity time graph must be 0 at that point, a quarter of a cycle in. After half a cycle, we can see that the acceleration now has its maximum negative value. Okay, so maximum in the other direction. So if it's a maximum negative value, that's when our velocity time graph must have its greatest downward slope, its greatest negative gradient. And we can see then at 3/4 of a cycle in, the acceleration is now 0 again, so we have no gradient, 0 gradient in our velocity time graph. And then 1 cycle in and we're back to where we started. We've got a maximum positive acceleration. So that's where we will have a maximum upward slope, a maximum positive gradient on our velocity time graph.